Okay, so this material that I wanted to cover is somewhat some miscellaneous stuff, but things that I wanted to point out to you and make sure that we understood. And I talked about this with a few of you, and one of the things that I realized that maybe we didn't discuss in any great amount of detail is what do constraints look like in Solidworks, okay? You guys have been doing this for assignment 3, and then we'll continue to do this for the rest of the assignments, is when we have something that is preventing movement, you have control in Solidworks to set that up. And in graphics in Solidworks, it looks like an arrowhead if translation is prevented. So if you want to keep it from moving in the X, Y, or Z directions, so translation, then it should look like an arrowhead. If you want to prevent a rotation from occurring, like it's fixed in the ground, then the rotations look like tails. Okay? And if you have both of them restrained, then it has the arrowhead on the front and the tail on the back. Both of those combine together to tell you that you have translation and rotation both restricted. Okay? So a fixed connection, if you remember back to statics, a fixed connection means no translations and no rotations in all 3 coordinate directions. So if we look at this, and they're all kind of jumbled up together, but we can see we have an arrowhead and a tail in the X direction. We have a head and a tail in the Y direction, and we have a head and a tail in the Z direction. So all 6 degrees of freedom are restricted for that constraint. So thinking about a flagpole that is buried into the ground so that it is not able to move in the X, Y, or Z direction, and it's also prevented from rotating in the X, Y, or Z direction. That's a fixed connection. We've talked about those in statics and strength of materials and so forth. Okay? This is a standard just menu click to create a fixed connection in SolidWorks. You don't have to do anything special. They also have a standard constraint that they call immovable. And thinking back to statics, what would an immovable restraint look like? What did we use in statics class that was commonly that condition?
It'd be a pin or like a ball joint.
Okay, so like a ball joint, right? Pinned in 3 dimensions, so a pin technically would just be 2 of those, right?
Yeah.
Because a pin is allowed to rotate on one of its axes. So a pin would just be 2 of these arrows, depending on which way the pin was oriented. So this technically would be best modeled as a ball and joint, or ball and socket type of connection. Okay, that would be an immovable. It's prevented from moving in the X, Y, and Z directions, but it is allowed to rotate in any of those directions. There are additional restraints, symmetry, roller sliding, hinge, that will have various combinations of these, and then you have the reference geometry one, which gives you the full control over each of those. So when you're inexperienced, probably just doing the fixed or immovable is easiest by all means, if those are appropriate for your circumstances. But we quickly get into needing to use the reference geometry to set those up.
I think I make those arrows bigger in SolidWorks because the nodes almost cover up the arrow completely.
Mm-hmm. I usually check it by zooming in and zooming out.
Yeah,
and
you can kind of
which
see
is
it, but like
kind of helps.
that node is like the same size.
Yeah, there probably is something that does that, but I honestly don't know what that setting is. But I agree that is a problem sometimes, is seeing exactly what that arrow is and which direction.
So it's on my version too, like the fix will show all 3 arrows, but when you go to like another side, like so for instance, like on this one, do the roller point, mine will only have 1 arrow in one direction no matter which way you click, like no matter which, I guess force or whichever way you click it, the arrow still stays vertical or horizontal or whatever, it just stays in one direction. Like I've looked up online to see if there's a fix for it, and somebody said it was SP.14 version of Solidworks or something. It's
Okay.
like a little bug in the system, but
So it's not displaying the restraint correctly.
yeah, it
Okay.
does it correctly, but the arrow.
Calculations are
yes,
correct, it just
calculations
doesn't
are
display
correct.
it correctly.
Yeah.
Okay.
So on some of my pictures, like the arrow will be going this way when it should be going this way.
Okay.
So, yeah.
Yeah, that can be confusing.
Yeah. Yeah.
Okay, well yeah, so there's where checking your answers to make sure you got the constraints in the right directions is gonna be important. Yeah. Okay. Yeah. All right, the other thing that we can do, if we want it to be a restraint like we're used to dealing with in statics, you just set the value to 0, meaning that it does not move at all. The other thing we can do, and I think we might have talked about this, is that you can put prescribed displacements on things. So occasionally you'll have an analysis where you know how much it deforms, and you're curious what kind of stresses does that create. And so you can actually put a prescribed displacement on the end of one. So what does that look like? Let's say that I have a cantilever beam, and I know that it's going to deform 1 inch. Okay? So you can put a prescribed displacement on the end where you tell Solidworks that it's going to be pushed down 1 inch. And then Solidworks will then figure out what the stresses are. So we can create loads by giving it deformed dimensions instead of actually giving the forces necessary to create that.
So if we don't know the force, you can just tell how much it deformed.
Right. And if you think about that, that might be easier for you in industry to figure out. So let's say that, I'm trying to think of an example. Let's say that, you know, we're dealing with a loading truck. You've got a truck, and we know that it's gonna back up to a dock, and there's gonna be a ramp on the truck. It's gonna stick out the back, and we know there's gonna be a little bit of gap between the ramp and the dock. And when the fork trucks come and roll onto that ramp, that is going to deflect down as the weight of the fork trucks come on there. Do we know how much weight that's gonna be? No, we really don't know what weight that's gonna be, but we know that when it hits the floor, it's not gonna deform anymore. So we could use that prescribed displacement, the distance between the ramp and the floor, to set up as the input for our model to calculate. Okay? Going back to the flagpole example I mentioned a minute ago, let's say at a 50 miles an hour wind, the flagpole bends over a little bit. We might be able to go out there and measure how much of it is it bending over. It'd be much easier to measure how much is it deformed rather than trying to figure out how much force is the wind creating on the pole. Okay, so that's a useful tool you might take advantage of. The other thing that I wanted to talk about in this is symmetry. And for assignment 6, one of the questions says use symmetry. Okay, so I want to make sure you know what that is. So symmetry kind of harkens back to the days when computers weren't nearly as powerful as they are now. Okay, so it's a method of reducing the size of the model so that it takes us less time to actually analyze it. As computers continue to increase in speed and power and capability, we have less and less incentive to try to make things as simple as possible. But you're probably going to have situations with complicated analyses where we don't want to model the entire thing because, one, we don't want to spend the time it takes to model the whole thing, or two, it's going to be so huge that it's going to take a long time for the Solidworks to solve the problem. Okay, so symmetry can reduce that, the time that it takes to come to an analysis. There's 4 different types of symmetry. The one that you're most, probably the one that you thought of when I say symmetry, is the reflective type. That's the really obvious type of symmetry. Okay, so reflective symmetry is like a mirror, that we can set up a mirror plane somewhere in the structure, and one side of the structure is exactly the same as the other side of the structure, and if the loads are symmetric as well, then the loads on one side of the structure are exactly the same as the loads on the other side. Okay? So the simplest to imagine, the simplest, the most familiar type of symmetry is going to be reflective symmetry with symmetric loads. We are assuming that the geometry is completely symmetric about that plane. The materials and elastic properties are symmetric about the plane, and my constraints are also symmetric. So airplanes are typically symmetric. I could take advantage of symmetry to model half of the airplane to really simplify the amount of material that I need to do. And that works as long as everything is truly symmetric and as long as the airplane is sitting, say, let's say it was sitting on the runway, then all 3 wheels are touching the runway and everything would be completely symmetric. Okay, that's not going to work if, say, the airplane is not symmetric. So if we're trying to model what happens when the plane loses half of its wing, well, that's not a symmetry condition anymore because the geometry is not symmetric. Okay? Or let's say we're trying to model what happens when it's coming in for a landing and the wheels under one wing hits, but the other wheels are still in the air. Well, that's not a symmetric problem anymore because we have loading conditions that are different on each side of the plane. Okay? So we're looking for geometry, materials, and constraints to be mirrored about the plane, and the loads can be either symmetric or what's called anti-symmetric. So let's talk about what that really means. Well, I thought it was the next slide. Let me jump ahead here. Anti-symmetric loads are going to look like this. So we have a load on one side in one direction, and then on the other side it's in the same position, but it's in the opposite direction. Okay, that's anti-symmetric loads. And that's going to change how we have to analyze the problem slightly. Okay, so just be aware of that. We'll get to that in a second. But let's go back to if the loads are symmetric on each side of the plane of symmetry. So this is a simple little simply supported beam, cantilever beam, I'm sorry, not cantilever, but a simply supported beam. We have a pin connection on one side, and this is showing a pin connection on the other side too, although in statics we typically make a roller on this side. We have symmetric loads. The loads are in the same direction on both sides. They are the same distance apart on both sides. And so I can simplify this problem by splitting it in half. And in doing so, I have to represent the constraints that are on that plane of symmetry. Okay? So let's look at that for a minute. So if I have that situation where I have a beam, simply supported, we have some forces. I didn't draw that terribly symmetric, so let's move this one over just a little bit. Okay, and these distances are the same. Try to use the same on the paper. These were labeled as A. PowerPoints, and then the distance to the center was labeled as B. Okay, something like that. When that deforms, what does that look like? What shape does that beam have?
Like U-shaped.
Smiley face. That was exactly the word I was thinking of, right? What were you saying, Eric?
Oh, U-shaped.
Okay, U-shaped. So the deformed shape is going to be something like that, right? Okay? If I cut this in the middle and I erase half of this, what has happened there on the end? So if I'm looking at this, so let's put some coordinates on here. Okay, we're going to call this the x direction, we're going to call this the y direction, and the z direction has to be coming out of the page. So when this is deformed, we have, did x change? So if we look at the piece of material on the end of this, has its x location changed? It hasn't, right? It's moved downward, but it has not moved in the x direction, right? So delta x is no, so x is equal to 0. Does the y change? Yes, it does. Does the z change? Not with the loading that we have on this, right? Okay? Does z change? No. So z is equal to 0. Actually, I'm going to change that a little bit. Because of the loading that we have here, the z doesn't change. But could we put a load on in the z direction and it still be symmetric? We actually could. So I'm going to erase that. I'm going to, does z change? And I'm going to put possibly. It doesn't because of the direction that I have the load set here. But we could put a force in the z direction, it could still be symmetric. Okay? So does rotation in the x direction? Is there rotation in the x direction? Could it still be symmetric? Now, with this given load, no. But if I had twisting about the x direction, could this still be symmetric? The answer is actually it could be. Okay? So we could have some torsion on this that is causing rotation about x. So I'm going to put possibly, depending on the loads that are applied. Okay? Rotation about y? Question mark. Okay, so y would be rotation this way. actually no. Okay? So if I think about this, my plane of symmetry is coming out this way, right? To have rotation about y, what has to happen? Material that is out here has to go this way, and material that is in the back has to go that way. Okay? So a rotation about y is not gonna, it's gonna break that plane of symmetry. Okay, so one way of thinking about this, think about my plane of symmetry as like this invisible boundary that I can't cross. Okay, so my material can move such that I don't break the plane, but anything that's going to cause us to break that plane is going to violate my symmetry. Okay? So if I think about that, if, let's use a physical object to see if we can illustrate that. So my plane of symmetry is coming straight out this way. Okay? So if I think about my beam here, here's my plane of symmetry. If I'm allowed to have rotations about y, it should be like this, right? This is a rotation about y. What happens? This corner moves this way, and this corner moves that way. And this corner is going to distort my perfect plane of symmetry. So I can't have rotations about y. Okay? Now, can I have rotations about x? Yeah, because notice my material does not break that perfect plane. Okay? So rotation about y, no. And so rotations about y are, have to be equal to 0. And then rotations about z, question mark. Going to be the same problem, right? Rotation about z was out this way. Z's going out straight out this way. So rotation about z is going to cause us to break that plane. Now this is a little bit hard to visualize. So you might have to sit here and think about this a little bit. Okay, but what I'm trying to show you is why we're allowed to move in some directions and not others. So going back to my example, I got my perfect plane going out this way. I can move my end piece here. I can move it in the y direction and not break that plane. I can move it in the z direction and not break the plane. I cannot move it in the x direction because it's going to break the plane. So my x directions are zeros. I can rotate it about the x axis without breaking the plane, but I cannot rotate it about the z or the y axis, which would be this way, rotations this way, and I cannot rotate it about the z axis, which would be rotations this way, all of which would break that plane. Okay, so rotations about z, no. So rotations about z is equal to 0. So if I wanted to manually set up the constraints in Solidworks using reference geometry, if I had a line of symmetry, what we would do is model half of the geometry, and then I would apply the constraints on the end of this of x is equal to 0, rotation y is equal to 0, and rotation z is equal to 0. And we can set up Solidworks so that we can specify exactly those constraints. Okay? And when I do that, then that is applying a symmetry constraint. And then I can model just half of this instead of the whole thing. Now, the honest truth is that Solidworks makes this easier for us because it has the ability to apply symmetry to a plane, and it figures out what those constraints are. But on a test next week, I might ask this question, and you need to be able to figure out which one of these are supposed to be 0 based on that plane of symmetry. Okay, so a couple things make this easy to remember. Okay, what is, as drawn, what is this plane? This is the YZ plane, right? Okay, this is the YZ plane. Notice Y and Z are the rotations that are 0, and the displacement that is 0 is the X. One that's not in the plane, the one that's perpendicular to the plane. So if I just give you some arbitrary plane, let's say the XY plane, what are going to be the constraints?
Z equals 0.
Okay, Z equals 0,
And X and Y rotation equals 0.
rotation X equals 0, and rotation Y is equal to 0. Okay? So it's not that hard to, you know, if you see the little pattern there, then it's not that hard to figure out for whichever plane you have set up. Okay, questions about that? So if you use the symmetry constraint in SolidWorks, it does this for you automatically. But if you need to set up symmetry yourself, you can also use the reference geometry and manually tell it which ones of them do you want to be 0. On the slide here, notice this says permitted motions. Okay? And I thought about changing this slide because I like to say which ones are 0 because that's what you're going to have to tell the software to do. The opposite of that is which ones are allowed. So what is allowed, Y is allowed, Z is allowed, translations, and the rotation about X is allowed. Okay, so this is opposite of what we've written up here. This is permitted, this is prevented. Okay, okay with that?
On the test, will you ask something like that, or like?
I would ask something like this. Most likely. Because that's the way you're going to have to put it in the software, so why not think of it that way? Okay? What is not allowed seems to make a little more sense to me. Okay? All right. If there is a force that is on the line of symmetry, then you need to divide that force by 2. Okay, so if I have a case where I have a force in the center and I want to use symmetry, if the force is 100 pounds, when you use the symmetry model, you do half the geometry, you're going to take that 100 pounds and make it 50 pounds. Otherwise, you're going to have too much force applied to your model. Now, if the force is not on the line of symmetry, like back the previous example, if both of these were 100 pounds, then you'd put both of these as 100 pounds. Okay, it's only when it's on the line of symmetry do you divide it by 2. Okay. Anti-symmetric restraints means that our forces are opposite directions on each side, and the effect is that it switches what's allowed and not allowed. It's the exact opposite of what we had done previously. So if my forces are reversed, then instead of this being 0 rotation or 0 translation in the X direction, now it's going to be, so this is symmetric restraints. If we do this with anti-symmetric, meaning that the load is removed, then my zeros are Y is equal to 0 and Z is equal to 0. Okay? The opposite things are true. So over here, X is equal to 0. Over here, Y and Z are going to be equal to 0. Over here, rotation Y and rotation Z are equal to 0. Over here, rotation X is equal to 0. And that's because the loads are reversed on the opposite sides. Now, I'm not going to dwell on that to a great extent because the number of times I've used anti-symmetric constraints in a model has been precisely, I think, 0. But it's out there if you ever have the need for it. Okay? All right. Another type of symmetry is called skew symmetry. Half rotation about a point results in self-coincidence. This is another one that's kind of obscure, and so I'm telling you about it, but the likelihood of you actually running into this is small, or at least the number of times I've used it is 0. So skew symmetry, notice if I put a point right here and then rotate this a half turn, half rotation, then it overlaps exactly this part. Okay, so that's a form of symmetry that you could utilize. Maybe if you're modeling something that has a lot of, like a turbine engine or something that has a lot of symmetry, you might find some situations where that applies, but unusual. Something that is very, very common, and this is something that is very, very useful, is when I have axial symmetry. Okay, this happens all the time, and this is very useful. And the reason that this is so useful is I can take three-dimensional geometry and cut it down to a planar problem. Okay, so rather than modeling, so this is a case where we have this particular example is we have an O-ring that is in blue here, the O-ring is in a slot, and then we have something that is compressing the O-ring, and we want to do a model of that. Okay, this has axial symmetry in that if I take a section anywhere along that, the geometry is exactly going to be the same. Okay, if I model this in 3 dimensions, this is going to be a huge number of nodes and elements because of having to do this, all of the solid elements around that whole thing. It's going to take quite a bit of time or a relatively large amount of time to analyze that. But using axial symmetry, I can reduce all of that down to just the cross section. Okay? So I can model the rectangle for this piece that's compressing the O-ring. I can model the O-ring as simply just a circle, and then the geometry of the groove. Planar, and all I have to do is tell the software that this is axis of revolution. Okay? And then I just model this, and then it will take it and apply the results around the whole thing to show you what it looks like in 3 dimensions. But it greatly simplifies the math, which means you get a result much quicker. So this is a 2D shape that represents a 3D model. So this is kind of showing what your output's going to look like this. This is the 2D results. And then the software will then rotate that around to show you what it looks like in a 3 dimensions type of thing.
So you just do a 2D sketch,
Yes.
and then you do
It's
some.
a 2D mesh, 2D sketch, and then you tell it that it's an axisymmetric thing. And then depending on the software, depends on what kind of output you get.
Yeah.
You know, some of them will show you what it looks like in 3 dimensions. Others just show you this. You just kind of have it in your head, kind of visualize what that looks like, wrapping it around 360 degrees. Okay? Solidworks has the ability to do that. So when you go to your study types, you have Axisymmetric that you can use. So that's a type of model that you can use in SolidWorks. And when you do that, then you just have to do the 2D geometry instead of drawing the 3-dimensional geometry. Okay? Now this works. Not only does the geometry have to be 360 degrees symmetric, but the loading does too. Okay, so back on this example, the O-ring, we're assuming that this is being pushed down all the way around equally. This doesn't work if you're pushing down with a force on one side but not the other side. That's no longer axisymmetric. Okay, so the loads have to be distributed all the way around as well. Oops, I'm going backwards. Sorry about that. All right, so you can set that up in SolidWorks when you define the study. You can tell it you want to use axisymmetric. The 4th type of symmetry is Cyclic Symmetry. This is kind of expansion of the Skew Symmetry. And again, this is one that is really obscure If I look at this really, really carefully, you'll notice that these could be represented as triangles. And I have the same triangle that's repeated 6 times around that shape. Again, you know, this is from years ago when, you know, great efforts were used to reduce the model as much as possible. Nowadays, we got enough power probably that we just model the whole hexagon and be done with it, kind of thing. Okay? But if you've got a really, really large model that you just have to reduce the size to make it possible to analyze, then this is another type of symmetry that you can utilize. Okay? So I'm just mentioning it to you. The reality of you using it is probably fairly small. Okay. I think we already talked about von Mises stress, right? But I put that in here again. I don't know that it ever showed up in the PowerPoints, so I wanted to make sure that you had that, you know, written reference somewhere for future use. Von Mises is based on the principal stresses for multi-axis loading. So it's a combination of the X, Y, and Z stresses. And the point of this is that if the von Mises stress equals the yield stress, we're expecting the material to yield. So it provides a really nice, concise way for us to check in 3 dimensions, is this thing going to be a problem? Right? Because the problem is, if I look at the principal stresses in the X direction, and let's say that they're 25,000 psi, I look at them in the Y direction and they're 15,000 psi, and I look at them in the Z direction and they're 5,000 psi, all of those are less than, say, the yield strength of 30,000. The question is, do those add up so that there's a vector in some direction that exceeds the 30,000? Von Mises tells us that. It combines all of the different directions into one number that I can then compare to the yield strength to decide if I have a problem with my structure. Okay? So the default output for almost all analyses is the von Mises because it gives you a really clear, direct judgment call of, is the stresses too high? Okay. So that was the PowerPoint I had scheduled for last week. We didn't do it because I felt like you guys needed to work on your assignments, but we need to get through this so we can do a test next week. Okay?